Hi, I'm Ryan Baker, and this is Big Day in Education. Welcome to the last video of the third week of class, where we'll discuss knowledge engineering, a method that's kind of, in some ways, in opposition to the kind of educational data mining and analytics methods I've been talking about so far, but in some ways is also a great complement to them. So knowledge engineering is where your model is created by a smart human being, rather than a computer that just exhaustively searches through all the possibilities. It's also called rational modeling or cognitive modeling. In the classical version of knowledge engineering, a knowledge engineer and a domain expert work together to model the construct. What they do is follow an iterative process where the knowledge engineer interviews the expert and then creates models based on what they understand about the expert's process and reasoning. They then go back to the expert and they go through the model and its implications with the expert. They get feedback from the expert on what they did right and did wrong. Then they enhance the models based on what they got as feedback from the expert, and they repeat the process. And they keep going through these iterative cycles of modeling and checking with the expert until both the knowledge engineer and the domain expert believe that the model has fully and accurately captured the expert's reasoning. At its very best, knowledge engineering can achieve higher construct validity than data mining and comparable performance in data. And even in some cases, it can transfer better to new data by capturing more general aspects of the construct. For instance, Luc Paquette applied a classical knowledge engineering approach to studying gaming the system, where he interviewed a domain expert who was experienced in recognizing gaming the system, and then engaged in that iterative process we've talked about to refine the model. He developed this model for the cognitive tutor system, but he was able to transfer the model with no modifications at all to the assessment system, and it still performed quite well. And models developed through data mining don't transfer between different systems nearly that well. I'd like to give an example of some really excellent knowledge engineering, and that's Vincent Alevin and colleagues' model of help seeking. Alevin's model, like I said, is prescriptive, and what it was is it's a model of how students should seek help in an online tutor, specifically the cognitive tutoring system. In this system, the student is first supposed to spend time thinking about the step. If it's familiar, then you say, do they have a sense of what to do? And if the student says, yes, I have a sense of what to do, then the student should try a step, should enter an answer. If the tutor says it's correct, move on, you're done. No need for help seeking. But if the tutor says it's wrong, then the student has to say, was it clear how to fix it? And if it is, try a step again. But if it's not, go back and ask for a hint. And you'll notice you can also get to this point of asking for a hint if it's not familiar at all. At this point, you ask for a hint, you read the hint. Now, there are situations where a student doesn't need to read the hint, and it can still be part of a good metacognitive strategy. A few years later, Ben Shih and Ken Katinger and Richard Shyness had this nice model which showed that some students actually click through the hints at high speed, get the answer, type it in, but then stop and self-explain it, kind of turning the hints into an opportunity for a worked example. But this wasn't part of Alevin's model at the beginning. It's not all that common a behavior. So Alevin said you ask for a hint, you should spend time reading it, and then if the hint was helpful, then you can go and try to solve the problem again. But if it wasn't, ask for another hint, and keep going until you finally get to a hint that's actually helpful. So Alevin combined this prescriptive model with a taxonomy of student errors in their help seeking, which included things like help abuse, and there were subcategories of it, things like clicking through hints, which is a subcategory of gaming a system. Also things like help avoidance, so a student needs help, but they don't seek it. Tri-step abuse, which included trying a step too fast, which is a subcategory of gaming a system again, and other things. So the point is that through very thorough study and theorization of this learning system, Alevin was able to come up with this model of how good help seeking occurs and of how bad help seeking occurs. This model was developed based on a pretty thorough process. First of all, Alevin and his colleagues did a thorough study of dozens of scientific articles. The resultant review paper, which was published in 2003, really landmark review in help seeking, reviewed around 300 different articles on how students seek help both in online and offline learning. So Vincent and his colleagues really got a deep understanding of the construct they wanted to model. Then they had years of experience in designing online learning environments. Including the team was Alevin and Katinger, who were involved in the development of cognitive tutors for years, and some of their cognitive tutors are still used by around 6% of U.S. high school students. Third, there was intensive study of log files of student interaction with the learning system. Alevin and his colleagues really kind of embedded themselves in the data and just studied it very deeply to really understand what they were trying to model. And plus, even better yet, they had experience watching kids use this educational software in real classrooms. Levin and Ken and Ido Roll and Bruce McLaren are not just armchair scientists. They actually go out to the field and they really watch how the kids are learning from their learning systems. So you take all these things together and you get a pretty good system. You get resultant models that are predictive of student learning and even predictive of student preparation for future learning. That's right, they can even predict whether you'll be able to learn later on. And specific aspects of the model correlate to data mine detectors of some constructs and improve the data mine models if they're added to them. So not only do these models capture the constructs, and capture the constructs in not the same way, but comparably to data mine models, but they can even capture some of the variance that's not captured by the data mining models, which is a great thing. So that's knowledge engineering at its best. Now let's talk about knowledge engineering at its worst. Knowledge engineering and rational modeling and cognitive modeling are sometimes used to refer to something different than this deep, reflective, high-quality, data-driven process. Instead, they're sometimes used to refer to making up a simple model very quickly, and then calling the resultant construct by a well-known name, and not testing on data in any way, and asserting that their model is the construct despite having no real evidence for that. This kind of knowledge engineering achieves poorer construct validity than data mining because there's no real evidence and no real attempt to really get great construct validity. And it predicts desired constructs poorly, sometimes even worse than chance, although you don't see that get published very often. And that's because they oversimplify often a complex construct. If you looked at a Levin's model of help seeking, it was quite complex. You have to have a complex model to really understand real phenomena that you see. And if you come up with something incredibly crude, it's not going to capture that. It may even fail to match it at all. And this can slow scientific progress by introducing false results. If you say that you've got a model of X, and your model of X is actually wrong, and you come up with results based on that, well, that's not what you should be doing in discovery with models. Doing discovery with models, we'll talk about it in the 8th week of class, with a really good model like a Levin's model, is a really smart thing. Doing it with a junk model, not so great. And this can even hurt student outcomes. If you take your model and you build it into a learning system, and your model's wrong, overly simple or just plain wrong, it's going to intervene at the wrong time, and that's going to hurt student learning outcomes. So how can you tell if knowledge engineering is bad? I mean, I've just said it can be great and it can be terrible. How can you tell if it's bad? Well, here's the thing. If a data mining model is bad, it's usually pretty easy to identify from the features, the validation procedure, or the goodness metrics. Sometimes even something's too good. Telling top-notch knowledge engineering from junk is a little harder because the hard work's in the researcher's brain and the process is usually invisible, at least in the final published paper. People who do these kind of knowledge engineering approaches often talk about their process only in passing, when actually that's the most important part of the whole thing. But look for very simple, even crude models of complex constructs, and you'll have a way of thinking, maybe I should be worried about this knowledge engineered model. That's my opinion anyways. Now, whether you use knowledge engineering or data mining, you should be testing your models on data in some fashion. You shouldn't just be kind of throwing it out there and saying you're done. Even if you can't get a direct measure like training labels, you can usually get some sort of indirect measure, predicting student learning, for example. When you look at a Levin's help-seeking model, he had some direct measures. For example, he used some of our same field observations of gaming to try to test his model. But even beyond that, he had measures of learning and could show that things like help avoidance and help abuse actually correlated to learning outcomes in valuable ways. To point out, it's not an either-or. Feature engineering is very closely related to knowledge engineering, and careful study of a construct is going to lead to better features and ultimately to better models. Even if you're a hardcore, dyed-in-the-wool data miner, you should still be thinking about some feature engineering values. Understanding your data, understanding the construct. That's going to make for better features. It's going to make for a better data mine model. Using feature engineering models as features in data mining models can also be a powerful tool. You can take something like a Levin et al.'s model, put in a data mine model. It's important to point out that it's not an either-or. It's not like you either have to use knowledge engineering or data mining, because some researchers have combined them. For example, Luc Paquette has used knowledge engineering to discover what basic operators domain experts think in terms of when they're recognizing a construct, and then he's used data mining to recombine them in a broader range of ways. And that led to better models than either approach alone. So another point is that it's not just data mining models that can benefit from knowledge engineered models. Knowledge engineered models can depend from some data mining. They can benefit from it. So for example, knowledge engineered models sometimes depend on cutoffs or numerical parameters that are hard to determine rationally. And you can fit these parameters using data. For example, in a Levin et al.'s model is the question of, okay, you avoided help when you needed it. What does needing help mean? It's based on how much you know. But what is too much? What is not enough knowledge? Is it a 40% probability of knowing the skill, a 30%, a 60%, a 20%. You could actually determine this empirically using data, and Levin et al., along with Ito Rowe, have done this. Bayesian knowledge tracing, which we'll talk about a lot next week, also does this. So, thank you very much for attending this lecture on knowledge engineering. Next week, we're going to talk about knowledge modeling. Not the same as knowledge engineering at all. Knowledge engineering is the knowledge in the modeler's head. Knowledge modeling is your model of the student's knowledge. It's going to be a fun week. We're going to talk about Bayesian knowledge tracing and other classic algorithms. I hope you'll join us next week. Thank you very much. I'm Ryan Baker. This is Big Data in Education.